Okay, in this video, we are going to use different utility function axioms to solve the problem. So when you have a problem like this, usually the first thing I would do would be to draw the decision tree for the problem that you have. So here we know the decision maker has two options. So option A and option B. For A, there are two possibilities with equal chance. And for B, again, there will be two possibilities with equal chance. The payoff in this case will be 20 here, 15 here, 40, and 10. And so that's a problem that we are trying to solve. In addition, we know that the decision maker will be indifferent between these two, either $15 or $40 and $10. The probability for each will be 0.36 and 0.64. Secondly, we know the decision maker will be indifferent between $20 and 40, 10 with probability 0.6 and 0.4. So how can we solve this problem using the two that we have right here? So when you focus on this one, if we know the decision maker will be indifferent between these two, obviously I know for this part the value will be equal to $15. And similarly, for this part, I know the value will be equal to $20 because the decision maker will be indifferent between the two. So the certainty equivalent will be $20. So what I can do next is to use substitution to replace anything I know on the left-hand side by these two decision trees. So if you focus on this one, we cannot do anything. Although the payoff will be 40 and 10, we have 40 and 10 right here, but the probabilities are different. But here we know the payoff will be 20 or 15. So what we can do next will be to redraw the tree. So let me start from the bottom part, 0.5 and 0.5, 40, and 10. On the top part, I have A with probability 0.5 and 0.5. $20 is equivalent to the subtree right here. So what I'm going to do is to replace this by 0.6, 0.4, 40, and 10. Bottom part, $15. I can replace this by 0.36, 0.64, 40, and 10. So at this point, you will realize that all the payoff we have here will be 40 and 10. So how can we simplify the tree right here? What you can do next is to use the compound probability. So basically what you can do will be, again, let me write down the bottom tree first because that was the easy part. On top, we have two layers of uncertainties, but what I can do is to combine the two because I only have two possible payoff, 40 and 10. So what's the probability that you get a 40? It will be 0.5 times 0.6 plus 0.5 times 0.36. In other words, the probability of getting 40 would be 0.48. Similarly, on the bottom part, if the probability for getting 40 will be 0.48, this one will be 0.52. Now, that's the final tree I try to solve. And remember, there's a one axis talk about when you have the same payoff. Here we have 40 and 10. We have a 40 and 10. The decision maker should choose the one that gives you the higher probability for the higher payoff. So 0.5 is greater than 0.48. The decision maker should choose B instead of A. So that's how we solve the first problem. So in this problem, we are trying to solve the decision maker's decisions, assuming that the decision maker's risk attitude follows the exponential utilities. Particularly, the one that we are trying to solve will be between C and D, where D will be 450 and C will be equal probability, where the payout will be 750 or $50. Okay, and also we know that the decision makers will be indifference between A and B, where A will be $500 and B will be 800 with 0.6 or 100 with 0.4. And the utility function will be the exponential utility functions. At this moment, you probably will try to plug in all the numbers into your utility functions because you know, okay, the exponential utility function will be 1 minus e negative of x divided by r. So maybe you want to plug in everything and solve r, then try to recreate the scenario to find out which one will be better. But one thing you need to remember, not every question requires you to do the calculations. In fact, if you try to plug in all the numbers into the utility functions, there's no way for you to solve the problem. Okay, so what you should do is to go back to the slide and to see if you missed anything. And if you remember, when we have the exponential utility functions, there's a property called constant risk aversions, which means that when the decision maker's wealth increase, his or her risk attitude will not change. So what I found out is that suppose the decision maker will be indifferent between A and B, then the decision maker should be indifferent between, let's call it A prime and B prime as well. So that's a tree, A prime, B prime. And if a decision maker is different between A and B, that means if I take $50 away from the right-hand side, I have 450 or with probability 0.6, 0.4, and 750 and 50. The decision maker should be indifferent between A prime and B prime. Okay? So that means for these particular questions, the values is equal to 450. So again, what you can do is to substitute 450 on the original tree. Let me erase that. So let me create a new tree right here, 0.6, 0.4, 750, 50. Okay, then we have the same scenario as the previous example. We have the same payoff, different probability. Obviously, we should choose the one that gives us a higher probability for the higher payoff. So we should choose D instead of C, which means D should be preferred to C. So in the very last exercise, we have 4 different options and we want to see which one is the best option for the decision makers. And this is not a very difficult question. The key that I'm trying to show here is that when you are dealing with the utility functions, most people think that, okay, I need to find the utility functions. I need to find the expected utilities. They forget the fact that you can calculate the certainty equivalent instead of just trying to find out the utility values. So that's one thing that you need to remember, especially in your exam. In this case, we know the expected value, we know the risk premium, and we also know the risk premiums will be equal to expected monetary value subtracted by your certainty equivalent. So that's the definitions. Risk premium will be the money you are willing to give up in order to get out of the uncertain situations. So obviously, we just need to calculate the certainty equivalent for each of this problem and know the value for each of the options. So for A, the expected value will be 500, risk premium will be 350. By the way, let me remove those terms a little bit. That means CE is equal to EMV subtracted by risk premium. Okay, so I have 500 subtracted by 350. That will be 150. For B, I have 510 subtracted by 370. That will be 140. For C, I have 490 subtracted by 320. 170. And for D, I have 500 subtracted by 400. I have 100. So the certainty equivalent will be the value of each options. So you just need to choose the one that gives you the highest certainty equivalent that will give you the highest value. So in this case, the answer will be option C.